So good afternoon. This is 504 Statistical Mechanics, May the 4th. And what we're going to do today is start the last chapter, slightly later than we would have done normally, on dynamics of statistical mechanics systems near equilibrium. So what our goal is severalfold. We want to look at what happens when a system is slightly displaced from equilibrium. And then we want to see how it approaches the equilibrium. So you can think of a displacement from equilibrium as being something that is imposed artificially, or you can think of it as being something that is, as the system is sitting there and fluctuating, it naturally goes to a state that is not the exact equilibrium state, and then will relax back. And we want to understand what those dynamics are. I want to teach you about Langevin equations, and in general, different levels of description for statistical mechanical systems. That are dynamical. So we're going to look at the dynamics of these fluctuations, and the important point here is the different levels of description. So not only do we want to see these different levels, but we also want to see how do we relate them. And this is going to be very important because what it's going to lead us to is to some very fundamental results in statistical mechanics called the fluctuation-dissipation theorems. So I hope to be able to get some way through this today. And the main way we're going to work on this is by looking at Brownian motion, which was really the first effort to understand this, undertaken by Einstein in 1905, and this is arguably one of his most profound papers in 1905. There's a lot of competition, but this was the paper that um, predicted, or at least convinced people that atoms exist. So let's get started straight away since we don't have very much time. So I want to start then with a section 3.1 on Brownian motion. And I'm going to kind of skip some of the history and the philosophy here. So let me just give you a quick cartoon picture of how one measures Brownian motion and what it is. So let's suppose that I have a mirror that is suspended on a thread like so, and then I fire in a laser beam of light, and then the laser beam gets scattered like so, and then I look at where the laser beam is on a mirror or on a screen like so, and I plot the position of the spot of the laser beam as a function of this distance, say from the center line x. And the idea is that this mirror is sitting there in thermal equilibrium, But if you do this experiment, what you will see is that if I plot x as a function of time, what, what you'll see is a graph that looks something like this, so something like that. And what we want to understand is what these fluctuations are and how to characterize them. So those are the main questions that we are going to be concerned with. So the way we're going to approach this is in three different ways. We're going to approach this by first of all making a mechanistic model. So one is I'll call it a mechanistic model, which is simply an assertion about what is happening, and that model we'll call the random walk model. Then we'll make a separate model, which I'll call a phenomenological model. And what that model is a sort of population average model. Which is sort of constructed by symmetry and conservation laws. And then the third model that we'll talk about is a stochastic differential equation model. And this is basically going to be what's called the Langevin equation. And I'm going to teach you how to do stochastic integrals and compute things from these models, from the stochastic differential equation model in particular. And it sounds complicated, but in fact, it's very easy to do, and we'll see that it tells us a lot of very interesting things. So I'm going to turn off the chimes, and let's get started then. So let's get started then with model number one, which is the random walk model. So the basic idea is why does the mirror fluctuate in the first place? Well, what it's doing is it is being buffeted by air molecules, and so the air molecules, if you took a snapshot, at one time you would see maybe a few molecules pushing it to the right, and then the next time you'd see maybe a few molecules pushing it to the left, and so it's going to be buffeted back and forth by these molecular impacts. And Robert Brown was a botanist who observed this phenomenon first in little particles of pollen that were jerking around in some very discontinuous way in water. And so the fact that we're going to model this sort of discontinuous jerky motion of pollen particles or the laser spot as a random walk due to molecular impacts. So let's draw our cartoon. So here is the particle, the macroscopic particle. So this might be a speck of pollen, or it might be the very small mirror, something like this. And then what we're going to imagine is that there are particles, air molecules, say crashing into it like this, and maybe some crashing into it like this, and maybe at this particular time there's a few more going to the right than there are to the left, and so these are the air molecules. And so what that's going to lead to is this in the next, if this is at time t, then at time t plus 1, it's going to then move over here, and now the particle will be like so. And let's suppose that at that particular time, we now look at where the atoms are, and so the air molecules are bumping into it, and perhaps maybe the situation looks like this. And so what's going to happen is that at the next time interval, time t plus 2, it's going to go over to here. And so on and so forth. And then maybe in the next time interval, it'll stay on the page. So maybe it'll go up to here, and this will be time t plus 3. And that's the trajectory that the particle makes. So the idea is that this is some kind of random walk. And what do we want to calculate? So the idea is that the trajectory is random, and we're going to say exactly what we mean by that, and unpredictable. So the best that we can hope to calculate is is what I'll call P of R and T, which is going to be that the probability that the particle is at the spatial position R at time t, given that it started at the origin at time t equals 0. So what the strategy is going to be is I'm going to now show you how to write down a differential equation satisfied by P, and then we're going to solve it. And we're going to construct that by recursion. And then we're going to solve that equation. So what we're going to do in our model is we're going to make an assumption. And what we're going to assume is that the particle at each time step the particle moves a fixed distance, which I will call a little l, and it does that in a random direction. So that is where the stochasticity comes in, just in the random direction. So let's work out the exact equation. So the exact equation starts off like this. Let's first of all draw the point where the particle is right now. So this is the point R, and it's there at time t. So if it's there at time t, then we know that on the previous time step, it must have been somewhere on the sphere of radius L, centered at this point, at this point R. So let me draw that sphere around like this. So that radius is of course L. And so let's suppose that the particle was somewhere on that sphere. So let's say that it was here. So this would be R minus L times the unit vector in this particular direction. And that would be at the time t minus tau. So, so when we talk about the time steps, we're saying each time step occurs a time interval tau. I'm going to just erase this and do it again. Then this is the picture. So what that means is that we can say that it was somewhere on this sphere with uniform probability at time t minus tau. So therefore, the probability of being at r at time t is the probability that you were at some point on this sphere at time t minus tau. And then in some unit vector n, and then the way that you can get to the point r is your trajectory could be like this, and then you go to here, or it could be you get to here, and then you go to here, or it could be that you do something like this, get to here, and then you go to there, and so on and so forth. And so what we have to do is sum up all those possible paths. So what we have to do is then sum up over all paths. And so the way we do the summing up of overall paths is very simple. We just say, well, the probability of being at r and t is then the probability of being at r minus ln at t minus tau times the probability that you go in just the right direction to get to the point r and t. And so that means that I have to sum over all the directions, and then I have to normalize by the number of steradians in 3 dimensions, which is 4 pi. So this thing over here is then summing over all directions in 3D, and normalizing by 1 over 4 pi. And the reason is that our distribution, our angular distribution, is uniform. So that's the picture. So this is an exact equation. So once it gets to the point r, there's a 1 over 4 pi probability that it will go in the right direction, and so we get this equation. So what's the next thing that we do? So this is exact, but our goal is to make a long wavelength description, what's called a hydrodynamic description. And what that means is that we're looking at long wavelengths and long times. And that's kind of consistent with our whole picture of statistical mechanics as being some kind of coarse-grained description of a physical system. So what is the way we do that? Well, what we're going to do is expand the P of R and T in an expansion, a Taylor expansion, and just keep the long wavelength terms. And so that means the lowest order in a gradient expansion. So what I'm going to do is I'm going to write this equation down in the following way. So here's P of R and T on the left-hand side, and then d2n over 4 pi. And then I'm going to do a Taylor expansion of the stuff on the right-hand side. So let me write that out. So what I'm going to do is I'm going to take this thing over here and do a Taylor expansion. So what am I going to get is this P of R and T minus L n dot grad P plus 1/2 L squared Ni Nj d2P by dxi dxj plus order L cubed, and then the second term, this term over here, minus tau dp by dt plus order tau squared, and then all of these things are evaluated at the point r and t. So let's have a look at what these terms are. So what we've done is I've expanded to lowest order in this gradient expansion, and you can see that I went to second order in space, and I went to only first order in time. And then the other thing I want to make a comment about is this notation here. So does everybody familiar with tensor notation? If not, let me just write it down. So we're using Einstein summation convention, which means Einstein summation over repeated indices. And so that means that when I write down, I'm only going to write this down once, Ninj d2p by dxi dxj. So what I mean by that is, first of all, I and j can be equal to x or y or z, which means 1, 2, or 3. And this means simply nx d2p by dx squared plus nx ny d2p by dy dx plus blah blah blah, a whole bunch of terms. Okay, so that's what this means. So let's now go ahead and evaluate the different terms in this sum. So the way we're going to calculate that is we're going to notice that the terms are different. The integral is just over n. And the integral over the unit vector n is the same thing as an integral over solid angle. So let's have a look at what the different terms are. So there's the first term, integral d2n over 4 pi. And what is that integral? So that one comes just from here. So this term over here does not involve n at all. And so therefore, it's just P of R and T is just a constant as far as the integral over n is concerned. And this one is designed to be 1. Okay, this is the integral over all possible angles, normalized by the number of possible angles, and so we simply get 1. The second term is this one over here. So the grad p is just some constant as far as n is concerned. So that is just simply the integral of d2n times the vector n divided by 4 pi. And this integral is equal to 0 because it's just summing over a direction. And then for every direction, there's an equal and opposite one. And so when we average over all directions, this vector is going to be the vector 0. Anybody got any questions about that? So if you like, this is an odd function multiplied by an even function, and so you get 0. So another way of saying that. Okay, so that's that integral. And then the third integral that we have to do is this integral over here. So again, as far as this thing is concerned, d2p by dxi dxj is just a matrix with labels I and j, so it's just a constant. So the thing that we have to evaluate is this integral d2n over 4 pi ni nj. And if this was a real class, I would now take a break for a few minutes and ask you to try and do that. But I'm not going to do that. I'm just going to go straight ahead and tell you what the answer is. So the answer is, anybody want to guess what the answer is? And just shout it out. Don't try to type it in. 5 seconds. Anybody want to guess? If you know or think you know, unmute your microphone and shout it out. Okay, nobody does. So I'll tell you the answer. It's 1/3 delta ij. So let me prove it for you. So the first thing is, let's set I not equal to j. So then that could be nx times ny integrated. So then what you can see is that in terms of the component nx and ny, then the integral is odd. So so whatever direction you go in, they will end up giving you 0. So then you say, well, what happens when I is equal to j? So then in that case we do the following way. So in that case, suppose I had, then that means that I is equal to j. So it could be 1, 2, or 3, or x, y, or z. So that let's look at that. So then we have the integral of nx squared. That's what it is equal to, times d2n over 4 pi. It's the same thing as the integral y squared, and it's the same thing as the integral of nz squared. So that means that if I add those things together, so I look at the integral of nx squared plus ny squared plus nz squared, then this thing is equal to this is equal to 3 times the integral of just nx squared, or 3 times the integral of ny squared, or 3 times the integral of nz squared. And this integral, we know, nx squared plus ny squared plus n squared, nz squared, this is equal to the absolute value of n squared, which is equal to unity. And therefore, because this thing is equal to unity, then this whole integral is equal to unity. And so therefore, what I've just shown you is that the integral of nx squared is equal to 1/3. And so because the integral is 0 when I is not equal to j, that means that therefore the integral d2n over 4 pi ni nj is equal to 0 if I is not equal to j, so that's delta ij, and when I is equal to j, it's equal to 1/3. So now that I know that, then I can now do the full integral, because if we go back to our differential equation. So this thing here is Nij times delta xi delta xj. So now what I have is 1/2 L squared 1/3 delta ij times d2p by dxi dxj. And in this expression, the i's and j's are summed over, and so this thing is 1/6 L squared times d2p by dx squared plus d2p by dy squared plus d2p by dz squared. So in the end, what I've just shown you, putting it all together, then what we get then is L squared over 6 tau del squared p is equal to dp by dt. And that equation is one that I'm sure you recognize. This is just the diffusion equation. And that's what the diffusion coefficient is in d equals 3. If it was in d equals 2, it would be a different value. It would be L squared over 4 tau in d equals 2 and L squared over 2 tau in d equals 1. Okay, so that's the equation. So now we want to know how to solve this equation. So in order to solve it, we need some initial and boundary conditions. So initially, we know that the particle is at the origin. So because we know that for a fact, that means that P of R and 0 is then just a delta function centered at the origin. So that's just delta of R. And then we need to know what the boundary conditions are. So the boundary conditions are slightly tricky. But where they come from is the fact that we need to know that P is a probability. And because it's a probability, that means that the integral of P of R and T at any time t over all space has to equal 1. The particle has to be somewhere. So that is the boundary condition, and this will rule out solutions that exponentially grow at infinity. So this basically requires that the solutions decay. But how they do that is not quite as obvious as you may think, and so I want to go through this in some amount of detail. And so the way we're going to do it is by using Green's functions. And the reason that I want to use Green's functions is because this is how we're not going to do it much in this course, but in future courses or in your research work, you'll use these techniques to understand the response and correlation functions of in physical condensed matter systems, for example. So the strategy is now to solve using Green's functions. And the reason I want to do this, apart from just teaching you the technique, is I want to show you how causality gets represented in this. So the reason we're doing this is, one, this is a standard technique, and this makes contact with the formalism of response functions and correlation functions. Sometimes when I teach this course, I give some lectures on those things, but this time we didn't do that. We spent the time instead on the density matrix. So that's one reason that I want to I'll talk about this, and the other is I want to show you about where causality comes in. So that's what we're going to do. So the basic the basic trick is first of all to make the equation inhomogeneous. So the reason that we want to do this is I'm going to solve this by Fourier transforms. But to do that, what I need to do is have a single equation which I can then Fourier transform. And right now the equation that we have is just a homogeneous equation. So Fourier transforming doesn't do any good. So the basic trick is one that hopefully you've seen before, which is to put the boundary and initial conditions on the right-hand side. So let me write down the answer, and I'll explain to you why it is the correct thing. So here is our differential equation, which should equal 0, but at time equals 0, so that's delta of t, is equal to a delta function at the origin, so delta of r. So this equation is the equation that includes now the initial condition. So this simply says over here that at time t equals 0, the particle was at the origin. So let's see if this is indeed doing the correct thing. So what is the proof of this? So when t is non-zero, the right-hand side is equal to 0, and so P satisfies the diffusion equation. So check mark for that. And what about when t is non-zero? Sorry, when t is equal to 0? Well, then we have to be a bit more careful, because we know that we can't define a delta function at t equals 0. So what we have to do, the delta functions are only defined in a measure theoretic sense. So what we do is we integrate from t is equal to minus epsilon to t is equal to plus epsilon, and then let epsilon go to 0. And what we're going to do is we're going to insist that the gradient of p is continuous for r going to 0 and t going to 0. And so when we do this, when we integrate this over the so we integrate both sides of the equation. And then if we do the same thing over here, then what this is going to give us on the right-hand side, this is just going to give us a delta of r. And then this term over here, this term will give us 0 because it's continuous as r goes to, as we take this limit. And this term, integral dt, that's just going to equal p. Sorry. And so I've got that on the left-hand side, this term integrated, integral of dp by dt is just p. And then we take that limit, and so this gives us that p of r at 0 is equal to the delta function. So everything is exactly as we expect. Okay, so this is just a nice way to put down the initial conditions into the differential equation. So step 2 is to solve by Fourier transform. So how do we do that? So what we do is we write p of r and t in terms of its Fourier variable. So we'll say it's integral of p of k and omega. So those are the Fourier variables. Then we're going to have an e to the I. I'm going to write it as k dot r minus omega t. It could be plus omega t, but I'm going to use minus just for the sake of argument, minus infinity to plus infinity. And then we integrate d3k over 2 pi cubed, and then we integrate d omega over 2 pi. And that defines the p in terms of its Fourier transform. So now what we do is substitute this into the differential equation. So we substitute it into equation star, and that's going to give us, and we do that, and of course on the right hand side, delta of r times delta of t, I can write that as 1 over 2 pi to the fourth, the integral d3k d omega e to the I k dot r minus omega t. So that's just the integral representation of a delta function. So now when I plug this into this equation star, the derivatives bring down factors of k and omega. And so what I get is that the integral of minus I omega plus d k squared times e to the I k dot r minus omega t, p hat of k and omega, d3k d omega over 2 pi to the fourth is equal to the integral d3k d omega 1 over 2 pi to the fourth. And then the Fourier transform of the delta function is just 1. And so therefore, what that means then is that p hat of k and omega is equal to 1 over minus I omega plus d k squared. So that's the Fourier transform of the variable that we want. And so now what I have to do is to calculate p of r and t, we have to undo the Fourier transform. So I have to do this Fourier transform. Okay, this is going to require us to do a complex calculation. And so the way we're going to do it is by first doing the integral in omega and then doing the integral in k. So the third step is we're going to do the integral in omega first. And to do that, we're going to use theorems from complex variables using Cauchy's theorem from complex variables. So I'm going to walk you through that now. So for the next few minutes, then what I'm going to be talking about is how to do this integral over here. Okay, and in this integral, k is just some number. It's just some constant, and omega is the variable that we're trying to do the integration of. So I'm going to start by making a cosmetic change to avoid you getting confused. I'm going to write p of r and t. I'm going to take this factor of minus I and move it up front. So I'm going to write this in the following way. I'm going to put an I out here. And then my exponential. And then once I've taken that I out, what's going to happen down here is I'm going to get omega plus I dk squared. So what's happened is the I factor has now gone to here. So why have I done it like that? Well, I've done it like that because I'm going to do this integral from minus infinity to plus infinity of omega. And I'm going to do this integral by contour integration. So this integral looks like this. Let me draw the axes. So this is going to be the real omega plane, and this is the imaginary omega knob plane axis, like so. And what we're supposed to be doing is we're supposed to be doing an integral from omega being a real number from minus infinity to plus infinity. So we want to do something like this. Now, how do we do that? Well, what I want you to notice is that this integrand here has a pole. Because when omega is equal to minus I dk squared, so let's put that pole over here. Then this integral becomes infinity. So what that means is I can think of two possible ways to do this integral. I can do it by going along here and then completing a arc at infinity along the curve that I'm drawing over here, like this. And this I'm going to call curve number 2. And then I could also do it by going along here like this, and then coming round like that. And this curve is the one I'm going to call curve number 1. And so the idea of contour integration is that I can figure out how to do an integral by counting how many poles are enclosed by a contour in the complex plane. So hopefully you've learnt about that in complex variable theory. And if you haven't, what I'm going to do in the next few minutes will be a good reminder. So the point is that we're looking at the complex omega plane. K is just fixed. So we're not talking about the integral over k. And curves 1 and 2 are possible ways to make a closed contour from the actual path of integration that we care about. So we then have to ask, well, why do we care about making a closed contour? Because the idea is that a closed contour integral is equal to 2 pi times I times the sum of the residues enclosed by the contour. And that's what Cauchy's theorem tells us. Okay, so that's why we're going to do it. So now we have to ask the question, which is the right contour to use? And the answer is that it depends on the time. So let's see how this goes. So the point is this, that the curves 1 and 2 are arcs of circles at absolute value of omega is going to infinity. So I hope you understand that. And so we can draw on this graph here that when we're evaluating those integrals, this is a distance r, and this is an angle theta that increases in this direction. So that's our picture of how we go round that contour integral. So the curves are arcs of circles, and the way we're going to choose which arc we use is which arc allows the boundary conditions to be satisfied. And the answer is going to be either 1 or 2, depending on the time. And in particular, what we're going to see is that what we need, we don't know what the boundary condition is, but remember we had this criterion over here, where is it? Back over here, that the boundary condition was that the P is a probability and therefore is integrable. And so that's going to be the thing that we're going to need. We're going to see that the on 1 or 2, the integral may be divergent. And then that would violate the normalizability of P of R and T. Okay, so that's the basic idea. So let's first of all consider the case when T is equal to 0, and let's work out what happens to these integrals. So first, let's suppose that we consider T is less than 0. So that means that on the arcs at infinity, I can write that omega is equal to r e to the I theta, just as we drew in this picture over here on the left. And as we go along this arc, what happens is r is going to infinity and theta goes from 0 to pi if we're on contour number 2, or it goes from 0 to minus pi if I'm on contour number 1. So in the integral, we have to look at the integrand, and the integrand has in it this factor e to the minus I omega t. So remember that k is just a constant, so we don't care about that. So now we're going to look at what happens to that factor as we go round the curves. Let's leave that over there. So now the question is, what happens to e to the minus I omega t as we go around the curve? So we can do this. We're going to do, remember, we're keeping t less than 0. So t is now just a number, -5 or something like this. And now we're going to go around contour number 1. So when we go around contour number 1, when we get to here at the bottom, so in the shaded region of contour number 1, basically what we have there is that theta is basically minus pi over 2, and therefore omega is basically minus I r. And so therefore what that means is the integrand is basically this. It's exponential of minus I times omega t, and omega is minus I, so that's minus I times r times t. So that is equal to e to the minus r times t, but t is negative, so this is e to the r times the absolute value of t, which is positive, and that has to be evaluated as r goes to infinity. And if that's happening as r goes to infinity, then you can see that the integrand diverges. And so path number 1 doesn't satisfy the boundary conditions. Okay, so good. So let's see now what happens when we look at contour number 2. So now we're going on contour number 2, and there, let's look at contour number 2. There it is. So as we go around here, eventually we get to this region up here, and on that shaded region, so in that shaded region, there theta is equal to plus pi by 2, and so that means that omega is equal to plus I times r, and so the integrand is equal to e to the minus r times the absolute value of t as r goes to infinity. And so the integrand, in other words, is finite. And that means that it satisfies the boundary conditions. And so what we conclude then is that for t less than 0, we must use contour number 1. And that tells us then what the integral is, because on contour number 1, there's no poles enclosed. So what that means is that the integral that we want, plus the integral over the arc at infinity, and it's this arc, is equal to 0. And so therefore, what we know then is therefore that P of R and T is equal to 0 for T less than 0. Okay, so now let's do this for T greater than 0. So what happens when T is greater than 0? So it's the same argument. But this time, the curve that must be used is curve number 1. Because curve number 1 now will be finite at the bottom part. And so now what we have to do is evaluate the contour integral. So for t greater than 0, we use contour number 1, and this has a pole. So now what we have to do is we have to compute the residue. So basically what we're going to say then is the integral from minus infinity to plus infinity, plus the integral over the arc at infinity, but now the arc is this arc with an enclosed pole, and now we have to evaluate what that thing is, and so that thing is equal to 2 pi I times the sum of the residues. And I'm going to put a thing here. I'm going to put a little question mark because I'm going to come back to that in just a minute. Okay, so that's what we have to do. So what does the residue theorem say? So the first thing is that on this integral, so on the arc, the integrand is 0 because it's exponentially getting smaller, and so because it's getting smaller, that implies that the contribution from the arc is equal to 0. So that means that the integral we want is just, so the thing that we want is this thing is just equal to this thing. So let's see what it is. So what is the residue? So the residue says take the pole, the integrand is e to the I k dot r minus omega t divided by omega plus ik squared. And so what is the residue So what we do, it's a first order pole. So it's just e to the I k dot r minus, and then omega evaluated at minus ik squared, like that. So to take the residue, you take the pole, and then you just simply cross out the pole, and then you set omega equal to the value at the pole, and that then gives you what the residue is. So then what you get is that the integral from minus infinity to plus infinity, the thing that we actually want, is going to be 2 pi I times e to the I k dot r, and then omega is equal to minus dk squared. There's a d in here. So this is minus dk squared t. And then there's one more thing, and that is that this integral has to be multiplied by a factor of -1. And where did this -1 come from? Well, it comes from the fact that we went round the integral, we went round the contour in the clockwise direction. And the theorem requires you to go round in the anti-clockwise direction, the direction of increasing theta. So therefore you have to put in a minus sign. So now let's put it all together. That says that P of R and T. So now let's go back to our final formula. So remember, in this final formula, we have this factor of minus I over here, which I put in order to keep track of things. So what that means is that minus I, that factor of I, will multiply this factor of minus I in here to give you a +1. And so now what you get is that P of R and T is the integral from minus infinity to infinity d3k over 2 pi cubed e to the I k dot r minus d k squared t. Sorry, this I've written this wrong. That's I. This thing does not have an I, and then this is true. This is true for t greater than 0, and it's 0 for t less than 0. So we'll come back to the physical significance of this in a minute, but this is the result. So step 4 or step 5 or whatever step we're on. Let me just see where we are. Okay, so step 4 is do the k integral. Now this one is much simpler, because you can see that this, if I take this integral, the integral is a product of integrals over kx, ky, and kz. Okay, because d3k is equal to dkx, dky, dkz. E to the I k dot r is equal to e to the I kx times x times e to the I ky times y times e to the I kz times z, and e to the minus d k squared t is equal to e to the minus d kx squared t times e to the minus d ky squared t times e to the minus d kz squared t. So everything just factorizes, and we can do the integral by completing the square. So it's just the Fourier transform of a Gaussian, and what you end up with is, and I'll let you do that for yourself. What you end up with is 1 over 4 pi dt to the 3 halves times e to the minus r squared over 4 dt. And that's true for t greater than 0, and it's 0 for t less than 0, and this is our formula for p of r and t. So I'm going to assume that you know how to do that integral, and if you don't know, send me an email. Let's just look at what this means. And the answer is, it shows you that we have causality. In other words, if we know where we started, we can predict the future, but not the past. And so the history is uncertain, is not unique. History is not determined. And this process is an example of a Markov process. And that really means that the future depends on the past only through the present. And that thing is called a Markov process. Okay, so now that we've done this, let's calculate something that we actually care about. So what we might ask is a very simple question. We might say, well, what is the distance that the particle moves? Well, the answer is that we know that if I compute the expected value of r, then that's going to be 0, because it can equally well go in any direction, and so on average it will cancel out. So the next thing that we should then calculate is the expectation value of r squared. So let's instead calculate the expectation value of r squared. In other words, what is the mean end-to-end distance? So what is this thing? Well, this is the integral of d3r, r squared times p of r, and we want to know this as a function of time. So we can just plug in our formula for p of r and t, just plug this in and do the integral. So I don't like doing integrals. I like doing them. I don't like integrating by parts. I like doing them by tricks. So let's do this by a trick. So what is the trick? Well, my trick is this. The integral I know how to do is the integral d3r times e to the minus a r squared. So you all know how to do that integral because it's just the product of a bunch of Gaussian integrals. And you know that the integral of a Gaussian integral from minus infinity to infinity is the square root of pi. And if there's an a in there, it's the square root of pi over a. So everybody knows how to do that integral, but I don't want that integral. I want to have this r squared in there. But you say, well, wait a minute, we're in statistical mechanics. And in statistical mechanics, every time we have to do an integral, we do a differentiation. So what you say is, well, look, I can evaluate that by just differentiating this integral with respect to a. That'll bring down the r squared. But of course, I have to normalize it, and I have to normalize it by d3r e to the minus ar squared. And then what is the value of a? Well, the value of a is just 1 over 4 dt, because that's the factor that I have in my exponential there. So now I just have to simply do that integral, and the the thing that we actually, this thing in here, the only thing that we're actually going to do, so that integral is equal to pi over a, and it's the 1/2, but there's 3 of them because it's in x, y, and z. There's 3 parts over here. So this is pi over a to the 3/2 power. So that tells you then that r squared is straight away 3 over 2a times pi over a to the 3/2 divided by pi over a to the 3/2. And so that is 3 over 2 times 4 dt, which is equal to 6 dt. So what we've just discovered then is that in a time t, if I wanted to compute the distance that's gone, the root mean square, displacement scales like the square root of the time rather than time itself. And that is Einstein's famous result. So we're going to leave it there, I think. Um, well, can I go on for another 5 minutes? Anybody have an objection? No objection. Go ahead. Okay, so let's go on. Let's go on to the next thing, because we spent a little bit of time at the beginning just getting started. So let me go on for just a few more minutes. So now what I want to do is I want to switch gears and talk about the phenomenological description. And for that phenomenological description, what we're going to look at is Brownian motion in a force field. And why we do this is something that will become apparent in just a minute. So this is going to be a different type of description. So now what we're going to do instead is we're going to consider instead an ensemble of random walkers. Okay, so now what I've got is I have my box, and now inside the box I have a whole bunch of these random walkers. So there they are. And they're non-interacting. But now that I've got a whole bunch of them, that means that I then have a density field. So I can replace this picture by if I have enough of them, by some density field that looks roughly like that. And so what I'm going to do is that we're going to call that density field n of r at time t. And if I have many of them, many walkers, then I get this density field. And so now the question that we want to ask is, what is the equation of motion for n as a function of r and t? So we can get that very simply because we know that particles are neither created and destroyed. And so we know that, first of all, we have particle conservation. And so what that tells you then is that dn of r by dt is going to equal to minus the divergence of a current of particles. So that's just particle conservation. The second condition, so that's the first thing. So the second consideration is that Brownian motion smooths out density gradients. So let's see this. So let's suppose I draw a picture for the system at some 3 separate times, like this. And then I'm going to just draw the particles. So let's suppose that initially they were concentrated like this. So that's at time t equals 0. So then some time later, what's going to happen is that they're all going at random in some random directions. And so some of them will have gone further out like this. So it'll be something like that. And then finally, if I go to very large times, they will be everywhere. So what that means is that here we have a very large gradient. And then a small one, and then none at all. So what that says is that the flow of particles tends to smooth out the gradient. So what we're going to say then is that we're going to say that J is then equal to something that's proportional to the gradient of n. And what it says is that the flux of particles is going to be proportional to the gradient. So the steeper the density of particles, the more they will move. But of course, they move in the direction of smoothing out the gradient. So there has to be a minus sign in front here because they reduce the gradient. And then there'll be a constant of proportionality, and we'll call that constant of proportionality d. So this equation here is a phenomenological equation that says what are the effects of diffusion. And it's not exact. It's a small gradient expansion. So in principle, there would be higher order terms like gradient of n squared, del squared n, and so on and so forth. So all of those terms are neglected, and the ones that we're going to keep is just the first order term, and this first order term has a name which I'm sure you all know. This is known as Fick's law. And Mr. Fick, actually, I think it was actually Fourier who wrote it down first, but anyway, it's called Fick's law. So that's our equation of motion, and so what that says is, now putting it all together, what we get is that dN by dt is equal to d del squared n of r and t. And this really just is the same equation that we got for the probability, but now this is an equation for the average density. Okay, so that's fine. So we know what the solution of that equation is because we just spent the last 45 minutes solving it. So the next step I want to talk about is I want to suppose that we now have an external field. So we'll call it an external force, which I'll call F. And what's going to happen is that the particle is going to move due to the force. So let's write down what does the particle do. So let's remind ourselves back at the beginning. We talked about our particle being like this, and now what's happening is it's still subject to these molecular impacts, like so. Okay, so there it is, but now it's also got this external force that is pulling it like so. So that's our external force. So what's going to happen is the particle is going to have two things. It's going to experience the drag from the viscous medium, and that's going to be ultimately due to the molecular impacts. And then it experiences the external force. So we can write down what the equation of motion is. The equation of motion for the particle is then m dv by dt is equal to the force minus the drag force, gamma v. So the faster the particle moves, the greater is the drag force, and so this gamma is the coefficient of friction. So if I wanted to solve that, I could write the solution down like this. So V is equal to 1 over gamma times F minus m over gamma dV by dt. And I'm going to assume that the drag is very large. And so if m over gamma is very small, which means a light particle or a lot high viscosity, then I can ignore this term over here, and then what I have left is just this term. And so it just simply says that the velocity of the particle is proportional to the force. And so we can write down that the velocity is proportional to the force, and the coefficient of proportionality is mu, and that's called the mobility. And that's just 1 over the friction coefficient. Okay, so then we have to ask, well, what is going to be the current density due to the force? So the answer is, well, if I've got a particle, a density of particles moving with velocity v, then we know that the current is just going to be the density times the velocity, which means it's n times mu times f. There's also the diffusion coefficient. So we also have the diffusion current, like we had before. And so that means that the total current density is J is going to be n times mu times f minus d times minus d grad n. And that's the total current of particles when you have a force. So then now we have to plug that into the continuity equation. And so that simply says that then dn by dt is equal to the divergence of d grad n minus n over gamma times f, and that equation is known as the Smolny-Trotsky equation. It's the generalization of the diffusion equation when you have an external force. Okay, so last thing for today, I want to look at the stationary states. So what I'm going to do is I'm going to suppose that the force comes from a potential. U of r. So that means that I can write down that F is equal to minus grad U of r. Okay, so then what we know is going to happen that as time goes to infinity, what's going to happen is that we should reach a thermal equilibrium. And dn by dt is going to equal 0. So this is just like what we did early on in the course when we did the principle of detailed balance. So what we know is going to happen is that n of r and t, as I take t goes to infinity, is going to go to the n equilibrium of r. And what is n equilibrium? Well, it's just going to be given by the Boltzmann distribution. So it's going to go as e to the minus u of r over kBt. So that's what we expect to happen. Okay, so let's see, is that true? Well, if that is going to be true, then we can ask what happens to the current. So what I'm going to do is I'm going to take this formula and I'm going to substitute it into here. So I'm going to replace n equals n equilibrium in equation star. So what I'm going to get then is this, minus d grad of n equilibrium minus n equilibrium times mu times f is equal to 0, because in equilibrium, I didn't say this, but I meant to say it. So this dn by dt is equal to 0 implies div j is equal to 0, and we're taking thermal equilibrium. And so by principle of detailed balance, we are going to take the solution where j is equal to 0. So we're not going to look at the non-equilibrium steady state. So now what happens is when I plug this into here, what I get is that d over kbt grad u of r minus mu grad u is equal to 0. And so the grad u's cancel. And so what I end up with is that d is equal to mu kbt, or if you like, kbt over gamma. And this result is what I wanted to get to. This is a very important result. This is called the fluctuation-dissipation theorem of the first kind. Or sometimes it's known as Einstein's relation. Einstein was the first person who did this calculation. And so what does this tell us? This is a really amazing result. And it's amazing for the following reason. What it says is that the friction, gamma, is related to the diffusion coefficient. And because you would think that the friction would be some arbitrary material parameter, the diffusion would be some arbitrary parameter, but in fact they turn out to be related, and they're related by temperature. So even though this is not in equilibrium, well, it is in equilibrium eventually. It's not in equilibrium, but it's approaching equilibrium. And so what we've learned then is that something microscopic, which is the diffusion, is somehow related to something macroscopic, which is the friction. And this friction is, of course, causes friction and Joule heating and so on. So this relates to dissipation. And diffusion is how particles move around. So this is related to fluctuations. And so somehow there's a connection between these things. Okay, so I'm going to end there. So next time we'll talk more about this connection. We'll talk about another way of seeing this fluctuation dissipation connection, but using the Langevin description. Okay, so I'm going to stop the recording.